All right, everybody, let's get started. The screen's coming on. So I know that the project and whatnot is a topic of discussion, and what I'll say is I'm going to try to make myself pretty available today, pretty available tomorrow. I will be in class on Friday, but I do kind of want to get through our matrix analysis example today because I am going to give you a homework on it that'll be due when we come back, the Wednesday we come back from break. So it's not due the Monday we come back, it's due the Wednesday we come back. And so what we're going to do is we're going to continue our analysis example by hand. I'm going to pull up some Excel to show you a little bit about some calculations in Excel, but I do kind of want to jump into this analysis example. Did everybody get the code? Everybody get the code? Because I'm going to show you the homework problem that you're going to get, and it's going to look confusing, but it's really not. Okay? Is everybody good? All right. So, by the way, if anybody needs any extra handouts for matrix analysis, I have them up here, the procedure. Okay? And by the way, let's talk about the procedure. So we didn't get very far in our example on Monday, so I would like to make some headway today. But again, we're going to go through the same process, the same procedure. So we're going to do this thing called assembly, which we've already talked about a little bit, where we're going to assemble the stiffness matrices for each of the elements into a big old spring matrix or a stiffness matrix for the whole system. And then we're going to write a force vector for the whole system. What we haven't yet talked about is how to solve for unknown displacements and then what we do to compute final results. That part is pretty straightforward, but it does require a little bit of matrix algebra. Some of that we're going to go through and sort of do together, but a lot of that you can do using Excel, okay? What I'll say is I'm going to bring up a little bit of Excel today to make the point. What we need to be able to do in Excel is we need to be able to multiply matrices and we need to be able to invert matrices. And there are two formulas to do that. The formulas to do that are mmult. And so you would do like mmult. You would have like array 1 and array 2. And I'm going to show you how these work today. And then there's also M inverse of an array. I'm going to show you how these work. Okay? I'm going to pull that stuff up here in a bit. I'm going to pull up the array calculations in Excel, but I want to make some headway on the example. So let me go back to the example that we were doing, and let's just sort of refresh everybody's memory. So again, this is an indeterminate structure because we're only considering forces in the x direction. And so if we're only considering forces in the x direction, we only have one equation of equilibrium, and that is that the sum of the forces in the x direction must be 0, but we have two reactions, so that makes it indeterminate. Okay? Now, a couple observations that we made for the problem. We said that the spring matrices, the stiffness matrices, will be 2 by 2 for each element, but then we said the whole system was going to have a 4 by 4 matrix. The other thing, and this is where we sort of ended the lecture, is we talked about the force vector, is we said that the force vector is going to look like this, okay? And what we said is that the reason why it looks like this is so we take each joint one at a time and we just write down the forces. So like for example on joint 2 we put a positive 300 since it's going to the right, and for joint 3 we put a negative 125 since it's going to the left, okay? Now likewise, for joint 1 and joint 4, I don't have a force. I put this R1 and R4. Why did I put R1 and R4? Because they are the reactions. And we don't know what those are yet. Okay? So the other thing I wanted to point out is what does this look like? What does the displacement vector look like? And what it's going to look like is this. So it's sort of like a checkerboard pattern with the reactions, because any time that there's a reaction, the displacement's going to be 0, and any time that there is a free degree of freedom, there's a displacement. We don't know what those are yet because we haven't figured them out. We haven't solved them yet, okay? But that'll come later, okay? Does that make sense? Does that idea kind of make sense? Okay. All right, so let me sort of recap where we left off last time. So where we left off last time is we said, okay, we're going to write a spring matrix or a stiffness matrix for each element. So for each element, we're going to compute EA over L. And so for element 1, we got a 100. Okay. So this is what our spring matrix looks like. And then what we do is we put those terms where they go in the big system matrix. And so this process of going from here to here is what's called assembly. Okay. So like, for example, if we go through and do this again for element 2, so let's just sort of take what happens with element 2. So if we do element 2, what's going to happen is we're going to do the EA over L. And it's going to be 3,000 KSI times 8 square inches over 120 inches. So I made it a point on this problem to use different materials. Okay. So when you go through and do this, you get 200 kips per inch, not 100. So when we write the spring matrix for the element, it looks like this. Is that okay? Is everybody okay with that? Now, for element 2, see, notice with element 1, remember this 1 and 2 that we put there? Because it's connected to degrees of freedom 1 and 2. Element 2 is connected to which degrees of freedom? 2 and 3. So this is going to be 2 and 3. 2 and 3. So when I translate this to a big old matrix for the whole system, what it's going to look like is it's going to look like this. Is that gray coming through? Can y'all see that? Okay. So in other words, what I'm doing is I'm just putting those stiffness terms where they go inside the big old stiffness matrix. So, and then what is assembly? Assembly is just adding all these up. Does that make sense? So, for example, we're just going to add term by term, term by term. And so we are going to have some places where they overlap. So like what's going to go in the 2, 2 position in the big matrix? It's going to be the 100 from here, the 200 from there, and it's going to be 300. Does that make sense? Everybody okay with that? That's what assembly is. So if you're wondering what assembly is, it's that. Okay, so we'll go ahead and do element 3. So there's only 3 elements in this structure. So EA over L for this is, 2,000. I think that's 9. Yeah, and this is 180. And so that's 100 kips per inch. So our stiffness matrix is just 100 minus 100 minus 100, 100. And then what are the codes going to be? So I'll call these member codes or matrix codes. So if this is 1 and 2, 2 and 3, what's this one going to be? 3 and 4. Okay. So 3 and 4, 3 and 4. So, that's too big. And so where are these terms going to go in the big old matrix? Like, if I had to put these terms in this 4x4 matrix, where are they going to go? Bottom right. They're going to go over here, right? Does that make sense? In this bottom right corner. So I'm just using gray numbers to sort of indicate like where there's zeros. And then we get that. Does that make sense? Okay, and so if I wanted to assemble this, if I wanted to do assembly, so basically what I would say is K for the whole structure is the sum. I'll say this. I'll say assembled. And so all I'm going to do is add these terms up. And so the way that I'll add these up is I'll just do it on a term-by-term basis. So like in the 1, 1 position, 100, 0, 0 makes 100, okay? And then in the 1, 2 position, I'd get negative 100. Here, I'm going to get 0. Here, I'm going to get 0. And so if you follow the pattern, it's going to look like this. Going to look something like that. And let me move this over here. Going to look like that. And that's going to be the stiffness matrix for the whole structure. In fact, let me scooch that. Actually, let's keep it under. Let's move that about like that. Okay. Does that make sense? Everybody okay with that? Okay. All right. So the best way of approaching this problem now is, let's go through our process. So part 1, the goal is to determine K, which we've done that, right? Part 2 is to determine F. We've done that, right? We've got F figured out because we have that. We did that at the very beginning, right? Because we've got F. So part 3 is basically going to say what are the displacements, okay? That's what we're basically trying to figure out. In a stiffness method, what you're trying to figure out is what are the displacements, okay? So let me show you how we're going to do that, okay? All right. Anybody have any questions? All right. Let's solve for the displacements. Okay, so let me show you what our system looks like right now. Okay, so right now, this is the system that we're trying to solve. K delta equals F. So what does that actually look like? Well, it looks like this. Yeah. This is the system that we need to solve. All right, that's our 4x4 system. And again, by the way, we're not going to have to solve any of these by hand. We're going to use Excel, okay? So what I want to do now is I want to apply boundary conditions, okay? So you all can do this, you know, like you all can do this sort of, you know, right there on your notes, but I kind of want a copy of the system because I want to show you what I'm doing and why I'm doing it. So let's apply boundary conditions. And so let me show you how I'm going to apply boundary conditions. Okay? Oh, I have a typo because this, that's supposed to be 0. Okay. So let me show you what I'm going to do. Okay? So the first thing I'm going to do is I'm going to eliminate this column, and I'm going to eliminate this column. Okay? And you might be going, like, why are you doing that? Because if you go through and do the matrix multiplication, this column, so like how do you do the matrix multiplication? Like how would we get this R1? We'd go that times that times that times that. And then how do we get the 300? That times that times that times that, right? Everything in this column is multiplied by this 0, and everything in this column is multiplied by this 0. So they're going to be multiplied by zeros if we were to carry all this out. So I'm just going to strike out the columns associated with the boundary conditions, okay? But I'm not just going to strike out the columns associated with the boundary conditions. I'm going to strike out the rows. The reason that I am striking out the rows is not because there's anything wrong with those equations, but mainly because I'm not going to use them right now. Instead, I'm going to use those equations later in part 4 when I solve for the reactions. And so what I'm going to do is I'm going to look at what I have left over, in which case I have that, 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 and this, and I'm going to say now I have 300, 200, 200, 300, I'm going to have this sort of reduced system, this smaller system that has been reduced to account for boundary conditions. And this is my KR and delta R. Okay? Does that make sense? Okay. Now, so what I need to do, so therefore, in order to solve this system, what I need to do is I need to take this as the inverse of this matrix times that. Okay. Now, by the way, this system, you could do this in your Casio, right? Because you could just do the 2x2 equation solver and put this, 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 and this, and it'll give you the answer. Okay. Now, what I'm going to do right now is I'm going to go ahead and give you the answer, and I'm going to say that when you do this, you get a value of 1.3 and 0.45. Okay. Now, some of you are probably like, okay, You want to tell me how you did that, Dr. Mike? Because you just sort of miracled that on the board there. So now what we're going to do is we're going to break out some Microsoft Excel, if I don't drop my keyboard. Okay? So if you have your laptop and you go to Blackboard, you will notice that on Blackboard, under the lecture notes for Excel, or for the lecture notes under matrix analysis, I posted this spreadsheet. So if you want to download it, you can work with me on this. Okay? What I'm doing here in this spreadsheet is I've got two spreadsheets. I've got one called array commands and one called 1D bar example. And just to sort of make the point, let me go to the slides a little bit. We're going to do our matrix calculations in Excel and not in MATLAB. If you want to do this in MATLAB, you're more than welcome to. I like using Excel for teaching matrix analysis because it makes the assembly process very visual. Okay, so we'll go ahead and do that. Now there are 3 array calculations that we're going to need in this class. Multiplication and inversing is arguably the most common. When we come back from break, we're also going to need another one, which is called a transpose. And if you're wondering what a transpose is when you have a matrix, and I got a nice little animation here. A transpose is what happens is when you take a matrix and you flip it about its main diagonal. We will see transposition when we come back from break. For now, we're not going to have to worry about it, but we will deal with matrix transposition later. And by the way, if we have a square matrix and we transpose it and it doesn't change the matrix, we say that matrix is symmetric. Okay? And a good example of a symmetric matrix is a stiffness matrix, because all the stiffness matrices are symmetric. Okay? But we'll deal with that when we come back. Okay. So if you go to the Excel sheet, what I've done is I put a few matrices here, and I said, okay, let's take these matrices and do some calculations. So just to sort of get you familiar with this, let me sort of show you something. Okay, so I have here 2 matrices here. So I have matrix A and matrix B. So we're taking a little bit of a pause from our in-class example. All right, so if I have matrix A and matrix B, okay, how would I add them? Okay, well, in Excel, you would probably think, okay, I can take this value plus this value and just copy that everywhere, right? That's how you could do that, okay? Have any of you ever tried this? Have any of you ever tried to go to this cell and just say equals all of this plus all this and press enter? And it does the whole thing? Now, you'll notice that it's worked correctly because if you put your cursor in any of these cells, Excel sort of like highlights it. It sort of puts a little halo around these cells to indicate that that's an array calculation. So one of the things in Excel is that if you try and change something inside an array, Excel gets angry, right? So whenever you do an an array calculation, you have to tell Excel, okay, wait a minute, like this is an array calculation, so just leave it alone. Okay, so I'm going to hit, delete this, and then it'll go back to it. So like, for example, if you wanted to do 7 times an array, just go into this first cell, equals 7 times matrix A, and just press enter, and it'll just do it. Okay, but again, you got to, not mess with anything inside the array. Does that make sense? So a couple things, if you wanted to do matrix multiplication, like for example down here, equals mmult of A comma B. Just press enter. Boom, there it is. Okay? Now, I'm not going to mess any more with this here. The only thing I'll tell you is this one here at the bottom, this looks kind of painful, the calculation of A transpose BA. We are going to have to do that when we come back from break. So I gave you sort of the answer if you kind of want to mess around with it, but you don't have to worry about it for this homework or for this lecture. Everybody okay? Okay, so let's go to the second tab and let's just sort of go back to what I've done so far. So I'm just going to sort of repeat what I've done so far on the board or the notebook. I'm going to do it here in Excel. So what do I have here? I've got each of the three spring matrices, and I've got them like 1, 2, 2, 3, 2, 4, right? So if I wanted, what I could do is I could say, okay, let's put these where they go in the system. I'm just equals that, enter. Like go to the very first cell, just say equals the whole thing and put it there. So notice how I put it where it goes, right? And so if I go to the K matrix, I go to the first cell and I'll say equals that plus that plus that. Press enter, boom. So see how assembly is real fast in Excel, real fast, you know? Pretty straightforward. Make sense? All right, does anybody have any questions about this? I see a few of you are trying it out on your own. Is anybody having any major problems? Okay. All right. So if I want to get to where I'm at here, so how do I do this? How do I get from K to K reduced and from F to F reduced? Well, what do? We knock out the rows and columns. So I'll just sort of in Excel take these cells and sort of, I don't know, make them gray just to sort of indicate that I'm going to be knocking out these rows and columns and knocking out these rows and columns. So this is going to be K reduced. This is going to be F reduced. Okay? All right. So how do I do this right here? How do I do this? Okay? So everybody watch up here. Watch up here. Okay? All right? So everybody pay attention. So what we're going to do is we're going to say, in order to calculate delta R, I take KR inverse times FR. Like that's what I'm doing. Okay? So what I'm going to be doing is I'm going to do an immult of two matrices. The first matrix is going to be M inverse of that, comma, and then the second matrix is that. And you'll notice that things look a little different inside the formula, because instead of saying like from G31 to H32, it's saying G31 hashtag, because it's basically Excel's knowing you're talking about this whole array. You're talking about this whole array. So it's the array is defined by the top left corner, and then there we go. So when you press enter, boom. Okay? Does that make sense? All right, does anybody have any questions? Okay. So I'll show you, since we've got this right here, I'll show you something that we can go ahead and do. Step 4 is to compute the final results, right? What are the two final results that we're going to compute? We're going to compute the reactions, and we're going to compute the internal member forces, right? So let's talk about the reactions first. So the reactions are really easy because all you have to do is take the original K matrix, okay? And then what we're going to do is go back to the big old delta vector. So the big old delta vector is 0, delta 2, delta 3, and 0. But we now know what that is, right? So that's going to be 0, 1.3, 0.45, and 0. Right? That's our delta vector. So what I'll do is I'll go into Excel and I'll basically put zeros there. Oh, wrong one. And put my values here. So now I have an actual displacement vector, an actual delta. Is everybody okay with that? And so what do you think will happen if I multiply that times that? What will happen? So this is kind of nifty. So let's multiply that and that. Now what do I get? This is interesting. What was F before? What was F before? it was R1, 300 minus 125, and R4. What are we getting now? We're getting minus 130, 300, minus 125, negative 45. So what does that tell you? R1 is 130 kips to the left. R4 is 45 kips to the left. Right? By the way, let's also ask something. What's that plus that plus that plus that?
0.
Why?
Because the direction must equal 0.
The sum of the forces in the x direction must equal 0, right? So now, see how easy it was to solve for the reaction? See how easy it was to solve for the reaction? So just to sort of formalize that back in the notebook, let's go to notebook land. So what we did in the notebook is we said, okay, let's go back to this. And we said, okay, let's solve for the reactions. And what we're basically saying is, whoop, hold on. What we're basically saying is that this is our system, but now all we're doing is we're going back to this value here and this value here, and we're saying, no, 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 no. We now actually have a value. We actually have a value. And so when we recompute this, we get negative 130 and negative 45. So what this basically tells us then is R1 is 130 kips to the left. R4 is 45 kips to the left. And I guess what we should also do, so this is an answer, right? I guess what we should also do is recognize that up here, we should say that delta 2 is 1.3 inches to the right, and delta 3 is 0.45 inches to the right. I mean, is that fair? You tell me. Does that make sense? Okay. All right, does anybody have any questions about this? Because I got one more thing I want to do with this problem, and then we're sort of done. Everybody good? Okay, all right. So let's go to the Excel because I kind of want to make a point about something. Okay, I want to determine the internal member forces in each of the bars. Sorry, I want to get the force inside bar 1, the force inside bar 2, the force inside bar 3. So the way that I'm going to do that is I'm going to just use this same F equals K delta time thing. So the way I'll do it is I'll basically say, okay, let's just do a little F1 is K1 delta 1. A little F2 equals K2 delta 2. A little F3 equals K3 delta 3. Okay? So let's just sort of work through how I'm going to do that. Okay? I already have the K matrices for each of the springs because I already did that, right? I already derived those, right? Because this is the K for 1, K for 2, K for 3. I need the D's. I need the deltas, right? So I'm going to need a delta 1. I'm going to need a delta 2. And I'm going to need a delta 3. Right? Now, I think the easiest way to do this is to go off of the member codes. Okay? Would we agree that delta 1 is going to be 1 and 2? This is going to be 2 and 3. This is going to be 3 and 4. So let me ask you a question. What value goes here and here? What is, let's go back to this. So this is 0, 1.3, 0.45, and 0, right? And this is what? 1, 2, 3, 4. All right? So tell me what goes here. 0, 1.3. What about here and here?
1.2,
And here?
0.45.
So see what I mean? We just form a displacement vector for every individual element. So let's do that. Now I'm going to put my keyboard back on. And so then what I'll do is I'll just do a matrix multiplication, right? I'll just do that times that, that times that, that times that. Right? Okay. So let's see. Let's do the first one. I'm kind of lazy, so I'm just going to copy and paste this. Okay. And I'm getting this. Okay. What does this mean? Can I erase this stuff here on this board? Can I erase this? Let's look at F1. Okay? What does F1 look like? F1 is negative 130, 130. Right? That's what that looks like. So if I were to draw those forces on a bar, what does negative 130 look like? What direction? So that would be like that, right? What does this mean? So I'm asking you, when I see a vector that looks like this, what does it mean the bar is experiencing? Tension. So this is 130 kips in tension. You see that? What about F2? F2 looks like 170 minus 170. So what's that look like? It looks, what, that's going to the right, that's going to the left. And so what does that mean? What did I tell you that you ought to do when you're reviewing your results in mass hand and you want the forces inside the truss members? I told you to, there was a shortcut that you could just look at the second number in mass hand. Remember I said you could look at the second number, and if the second number is positive, it's tension, it's negative, it's compression. These forces have to be equal and opposite. They have to be equal and opposite, right? So, does that make sense? So, can I just summarize? Let's just take a step back. Let's go back to the original problem. In a structural analysis, what are the goals? What do we typically try and find when we do a structural analysis? Let's see. So let's just sort of put this on the board. And by the way, all this stuff here on the board, I'll put in the notebook in a bit. Okay? But what are we trying to figure out? We're trying to figure out the reactions. Isn't that what we're trying to figure out when we do a structural analysis problem? But don't we know that? Don't we know that R1 is, what is that? It's 130 kips to the left, and R4 is 45 kips to the left? Don't we know that? What else are we trying to figure out? What are we trying to figure out? Like if this was a truss, member forces? Well, don't we know that? Don't we know that element 1 is 130 kips in tension. Element 2 is 170 kips in compression. What's the deal with element 3? What's element 3?
45.
45 kips in compression. What else are we interested in when we perform a structural analysis? Maybe joint displacements? Like this? I guess my question is, didn't we just solve everything? Like literally everything in the entire structure? One method, one approach, it's all done. All of it, the entire problem. Everything that we would ever want to find out about that structure is done. We know the reactions everywhere. We know the member forces everywhere. We know the joint displacements everywhere. That is why, and I guess my other final point is, and I hate to bring up MATLAB, because I know that MATLAB is the bane of your existence. But be honest with me, it would be easy to write a computer program to do this, right? All you would need to tell it is, for each element, you need to know what the E, the A, the L is, and how it connects, and you need to know the forces applied on each joint and where the boundary conditions are. And it would systematically go through and solve the whole problem. Does that make sense? That is what MassCAN is doing in the background. That's what it's doing. That is matrix analysis in a nutshell. If you understand that, guys, I took multiple classes on this in grad school. I've been doing this for, I've been doing this for years. And I'm telling you, if you understand this, you understand the most complex matrix analysis you could do, because it's just this and more. So, let me give you an example. What is the difference between what we've been doing now and trusses? And I'll give you one answer. Trig. I'm kidding. I kid you not. The only difference between this problem and a truss analysis is the inclusion of trigonometry. That's it. If you understand this, you understand how to do a truss problem. And we're going to talk about that when you come back from break. How to extend this to a truss analysis. What's the difference between this problem and beams? Well, with beams, you can have loads on the members instead of loads on the joints. So it makes the construction of the F vector a little bit more tricky. But it's all the same procedure, you know? Maybe the K matrices are different, but it's the same idea, okay? Does that make sense? That's matrix analysis, ladies and gentlemen. And with that, I kind of want to show you your homework. And I want to allay your fears, okay? So, this is your homework assignment, okay? And it looks scary, okay? But it really isn't, okay? So I want to sort of make the point. So what we have here is a system that goes in the X direction, okay? But it looks kind of scary, but it won't look scary as if you just keep this idea in your head. So there's a series of masses and a series of springs, okay? I want you to treat the masses, these rectangular blocks, these are the joints, these are the nodes, okay? The springs, those are the elements, okay? So for this problem, node 1 and node 6 are restrained, okay? So the idea is I've given you joint loads, I've given you restraint, I've given you elements, nothing changes, okay? I'll do you one better. If you go to the bottom, I'm even giving you the EA over L for every joint, okay? So let me give you an example. Let's take, so this would sort of be like my, like my hint for the problem. So let's take element 4, okay? So element number 4, what do we have? We have a K value of what? 5, right? So for element number 4, that's going to be your stiffness matrix, just 5s. And then where is element 4 in the system? Here and here. So the codes are going to be like 3, 5, 3, 5. Okay? So what does that look like in the big old system? So by the way, how big is the whole matrix going to be? How many nodes are in the whole system? There's 6, right? So what's it going to look like in the whole system? It's going to be, 1, 2, 3, 4, 5, 6, 1, 2. I'm going to fill it with zeros right now. Okay, so what do we've got? We've got 3 and 5. So we'll say there's where it goes. That's it. That's all there is to it, So it looks complicated. It's really not, I'll give you another one. What does the, let's look at the F vector for the whole system. So R1 and R6 are going to be unknown. Okay, what's the load on joint 2? So 5. What about joint 3? Is there anything on joint 3? 0. What about joint 4? 2. What about joint 5? Boom. It's not that hard, I'm not wanting this to be very challenging. The idea behind this homework is so you understand whenever you run a matrix analysis, whenever you do a computer analysis of a structure, to get an understanding of how the software works. Okay? Does that make sense? All right. What I will do is I sort of hopped around a bit between Excel and the notebook. So what I'm going to do in the notebook is fully transpose the calculations so that you see, in case you go back to the notebook, like, hey, how did he do that? So that everything I sort of like put on the board is in the notebook. I probably won't do that today, but I will do it so that by the time you start the homework, you'll be able to do that. And for this homework, you can turn this in Excel. You can turn the homework in Excel. Does that sound good? All right, I'll be here Friday, and I'll be around for the next couple days if you need help with your project. But other than that, if I don't see you, y'all have a wonderful break. So.